The pH of a solution is the negative of the logarithm to base 10 of the hydronium ion concentration or the hydrogen ion concentration. The hydronium ion concentration or hydrogen ion concentration is equal to 10 to the power of negative pH. The pOH of a solution is the negative of the logarithm to base 10 of the hydroxide ion concentration. Hydroxide ion concentration is equal to 10 to the power of negative pOH. pH plus pOH is equal to 14.00. Ka times Kb is equal to Kw. For a strong monoprotic acid HS, hydrogen ion concentration is equal to the concentration of HS. pH is equal to negative log of hydrogen ion concentration. For a weak monoprotic acid HW, hydrogen ion concentration is not equal to the concentration of HW. We use the ICE table to calculate the hydrogen ion concentration. Then we use pH is equal to negative log of hydrogen ion concentration. For a strong monobasic base, BOH, hydroxide ion concentration is equal to BOH concentration. pOH is equal to negative log of hydroxide ion concentration. For a strong dibasic base, BOH2, hydroxide ion concentration is twice that of the concentration of BOH2. pOH is equal to negative log of hydroxide ion concentration. For a weak monobasic base, WOH, the hydroxide ion concentration is not equal to the concentration of WOH. We use the ICE table to calculate the hydroxide ion concentration. Then we use pOH equals negative log of hydroxide ion concentration. To find the pH of a base, we use pH is equal to 14.00 minus pOH. Percent ionization is a measure of the strength of an acid or a base. The greater the percent ionization, the stronger the acid or base. The percent ionization of acid HA is equal to the equilibrium concentration of hydrogen ion divided by the initial concentration of HA times 100%. The percent ionization of base B is equal to the equilibrium concentration of hydroxide ions divided by the initial concentration of B times 100%. A strong acid has a weak conjugate base. A weak acid has a relatively strong conjugate base, stronger than the base on the opposite side of the equation, that is, on the same side as the weak acid. A strong base has a weak conjugate acid. A weak base has a relatively strong conjugate acid, stronger than the acid on the opposite side of the equation, that is, on the same side as the weak base. The equivalence point of a titration is when stoichiometric quantities of acid and base undergo complete neutralization. The end point of a titration is when the color of the indicator changes. For a titration between a strong acid and a strong base, neutralization occurs but hydrolysis does not. The equivalence point occurs at pH is equal to 7. The steepest part of the curve occurs when the pH range is between 4 and 10. For a titration between a weak acid and a strong base, both neutralization and hydrolysis occur. Only the salt's anion, that is, the weak acid's conjugate base, hydrolyzes to produce OH-. The cation of the salt is stable and doesn't hydrolyze. Equivalence point occurs at pH is greater than 7. The steepest part of the curve occurs when the pH range is between 7 and 10. For a titration between a strong acid and a weak base, both neutralization and hydrolysis occur. Only the salt's cation, that is, the weak base's conjugate acid, hydrolyzes to produce hydronium ion or H+ ion. The anion of the salt, which is the strong acid's conjugate base, is too weak of a base to hydrolyze. Equivalence point occurs at pHs less than 7. The steepest part of the curve occurs when the pH range is between 7 and 3. An appropriate indicator for titration is one in which its pH range coincides with the steepest part of the titration curve. A buffer solution is one that resists pH changes when small amounts of acid or base are added.